our group will be presenting question 1, which requires us to find the coordinates of the stationary points of the given curve. We also need to determine the nature of each stationary point and sketch the graph of the curve. In this presentation, we will apply the concept of differentiation to find the first derivative of each function. By setting the derivative equal to 0, we can determine the stationary points. Then, we will use the second derivative test to identify whether the stationary point is a maximum point, minimum point, or point of inflection. Finally, we will sketch the graph to clearly show the shape of the curve and the position of the stationary points. Through this question, we aim to understand how differentiation helps us analyze the behavior of curve, which is very important in engineering applications such as optimization and system analysis.
Now I will explain question 1. We are given the function f of x equals x squared minus 6x plus 8. First, we find the stationary point by differentiating the function. When we differentiate x squared, we obtain 2x. When we differentiate negative 6x, we obtain negative 6. The constant 8 becomes 0 after differentiation. Therefore, the first derivative of functions is 2x minus 6. Next, to determine the stationary point, we set the first derivative equal to 0. We solve the equation 2x minus 6 equals 0 and obtain the value of x equal 3. This means the x-coordinate of the stationary point is 3. After that, we substitute x equal 3 into the original function to find the corresponding y value. When we calculate 3 squared minus 6 times 3 plus 8, we obtain negative 1. Therefore, the stationary point is 3, negative 1. Next, I determine the y-intercept by substituting x equals 0 into the functions. When we substitute 0, the value of the function becomes 8. Therefore, the y-intercept is 0, 8. Then, we find the x-intercepts by setting the function equal to 0. We solve the quadratic equation x squared minus 6x plus 8 equals 0. We factor the equation into two brackets and obtain x equals 2 and x equals 4 after solving. Therefore, the x-intercepts are 2, 0 and 4, 0.
For this graph, we take the point open bracket 3 and negative 1 close bracket as our lowest point or the minimum point. Next, we mark open bracket 2 and 0 close bracket and open bracket 4 and 0 close bracket from the x-intercepts, where the graph hits the horizontal line. Then, we use open bracket 0 and 8 close bracket from the y-intercept to show where it crosses the vertical line. Finally, we connect all these points to form a perfect smile or a U-shape.
Now is question 1b. We are given the cubic function y equals 2x cubed plus 3x squared minus 12x plus 7. First, I differentiate the function to find the stationary points. When we differentiate 2x cubed, we obtain 6x squared. When we differentiate negative 12x, we obtain negative 12. The constant 7 becomes 0 after differentiation. Therefore, the first derivative of the function is 6x squared plus 6x minus 12. Next, we set the first derivative equal to 0 in order to find the stationary points. So, we solve the equation 6x squared plus 6x minus 12 equals 0. Then, we simplify the equation by dividing everything by 6, which give we x squared plus x minus 2 equals 0. After that, we solve the quadratic equation by obtain two values of x, which are x equal 1 and x equals negative 2. Then, we substitute these values back into the original equation to find the corresponding y values. When we substitute x equals 1 into the original function, we obtain y equals 0. When we substitute x equals negative 2, we obtain y equals 27. Therefore, the two stationary points are 1, 0 and negative 2, 27. Next, we use the second derivative to determine whether the stationary points are minimum or maximum points. When we differentiation is first derivative, we obtain the second derivative, which is 12x plus 6. Then, we substitute x equal 1 into the second derivative and obtain a positive value. Since the result is positive, we have confirmed that the point 10 is minimum point. After that, we substitute x equals negative 2 into the second derivative and obtain a negative value. Since the result is negative, this confirms that the point negative 227 is a maximum point.
For the cubic graph, we simply plot the points from the early solution. First, we take point open bracket negative 2 and 27 close bracket as our highest peak on the left side. Second, we take point open bracket 1 and 0 close bracket as our lowest value that touches the x-axis. And third, we use point open bracket 0 and 7 close bracket from the y-intercept as the crossing point on the vertical axis. By joining these 3 points, we get a smooth S-curve or a wave shape.
A stationary point is a moment of perfect balance on a curve where the rate of change is exactly zero. Think of a ball thrown upward. At its highest peak, for 1 split second, it stops moving before falling back down. In math, this is where the gradient is flat. Stationary points are the key to optimization, finding the best possible versions of a design. Physics, identifying the point of equilibrium in a moving system. Business, locating the maximum profit or minimum cost on a financial graph. AI, finding the global minimum of an error function so computer learn accurately. In conclusion, our analysis shows that stationary points are fundamentals to engineering optimization. By finding where the derivative is zero, engineers can identify critical limits. Essentially, stationary points allow us to move from making things work to making things work perfectly.